This is the second of videos showing the KINCALC operations, and in this video I will teach you how to calibrate your spreadsheet, going through the response factors for the different gases, twin peaks for nitric oxide, the use of ECD and TCD for N2O detection at low and high concentrations, and how you compensate for the leakage of oxygen and nitrogen and the loss of sampling. I start with a spreadsheet where I've already inserted my raw data, and I've done my job with the material sheet, putting in the names for the treatment of the different vials. I have my standards down here, and I've put the right liquid volumes for each of the vials with bacteria, and 0 for my standards because they are empty vials. That's absolutely essential before we start. And as you see, my standards for calibration are number 25 and 26 and 27. So the first thing I do is I go to master, and I take in one of my standards, and I start with air, and I know that my air standard contains 210,000 ppm of oxygen and 780,000 ppm of nitrogen, and they aren't exactly right here. Sometimes you get in some for some robots the default values in KINCALC are completely crazy compared to this, so you can get any number you want. You can't be anywhere near in some cases with the default values, and you have to set the right calibration factors. So the first thing I do, I look at the oxygen peak for my air standard, and I check that it's stable throughout the first readings, and that is actually quite important, that the first reading is not an outlier. Sometimes you get outliers with robots, even if they are automatically injecting things, and things should be quite stable. Sometimes you get the wrong readings. You can mend that by reintegration, but sometimes you can't because you have had problems with the injection. So in this case you see that there's a nice decline with sampling for the peak area for oxygen, so I can use my first one, which is where I can expect that this contains 210,000 ppm. So in an empty cell up here, I write equal 210,000, and I divide that by the peak area. Now that's 3.71 times 10 to the minus 3, and I copy this and put it into my response factor for oxygen, ppm per peak area, and mind you, you must paste this as value, not as a formula, otherwise it changes with the vials. So now we have almost the correct oxygen value, not exactly, and the reason for that is the 0 offset for oxygen. If that had been 0, I can do that now to show you. I will get 210,000 ppm in my first sample. Now I'll get back to the 0 offset. We actually need that for correct calculations of low oxygen concentrations. But as I said, I will get back to that. So we will do the same exercise with nitrogen. In most cases you will have identical ppm per peak area values for nitrogen and oxygen because the two gases are almost identical with respect to thermal conductivity. But in our design of the new robot, there is a ramping up of flow rate between the two peaks, and therefore then we have different response factors. So we do the same exercise again, but this time 780,000 and divided by the first peak of N2, get a number which is different from that one, and we copy that onto the N2 response factor, and again paste it as value, not as a function. We start at 780,000. Now there is one more gas and response factor that we can use the air standard for, and that is the electron capture response for N2O. Remember that in most robots use two detectors for N2O, a TCD detector for high concentrations and an ECD for low concentrations. The ECD is fabulously sensitive, but it has a lousy linear range, as illustrated in this graph here. This is the detector signal. This is the N2O concentration. It's almost or practically linear up to a certain limit, and then it levels off like this. Whereas the TCD is linear over a very wide range, but it has a lousy sensitivity. And that means for samples with low concentration, we measure it with ECD, for high concentration with TCD. And now we shall calibrate the ECD detector, because my air standard contains 0.58 ppm of N2O. And you can see that this low concentration is not detected by the TCD, but it is detected by the ECD. So we do the same exercise again, right, equal to 0.58 divided by the first peak area, and we get a response factor for the ECD. Copy that one, and you go to the ECD response, which is here, and again I repeat this over and over again, paste it in as value. Now we have 0.58 ppm of N2O to begin with, and then it's going down with dilution as we would expect. Now the next thing you want to do with N2O is to calibrate the TCD. And for that you need a sample with higher concentration, and that is vial number 25, which is what I call my high standard. And that is now having detection. Both detectors will detect N2O, but the ECD will be outside the linear range, and we have to use the TCD. We shall calibrate the TCD, and I know that my standard contains 150 ppm, so I write 150 and divide it by my first TCD signal, and I get a number again, and I put this into TCD response again as value, and now you see I start at 150 ppm. Now is the time to explain to you how the spreadsheet is distinguishing between the ECD and the TCD. The spreadsheet simply, if you look at the formula in ppmv, there is an if statement here. If E26, which is the TCD signal, times the TCD response factor is lower than the limit, it uses the ECD, otherwise it uses the TCD. So in this case it is not, and we can use the TCD to detect it. If I had put the lower limit for TCD up here to 200, the calculation of N2O would use the ECD signal, and it would be much too low, simply because we are somewhere here, and the ECD signal is way outside the linear range. So we want this limit to be as low as possible, but not lower than the level that allows your TCD to adequately quantify the N2O. The last thing that we want to do is to calibrate the CO2, and the CO2 concentration in my high standard is 10,000 ppm. So I write 10,000 ppm. That should be it. Divided by the first CO2 peak. And again, paste it for the CO2 response. And I start at 10,000 ppm of CO2. The next thing I want to do is to set the sampling volume right. Remember that when a robot in operation is taking a sample out of the vial, injecting it into the GC and the nitric oxide analyzer, returning the same volume of helium into the vial. That's what I call the sample volume. At the same time, there is, if the vial is anaerobic and free of N2, or almost free, there will also be a significant small leak of nitrogen and oxygen through the tubing and through membranes on the way from the sampling needle to the GC and back. And that sends a tiny little bit of oxygen and nitrogen into the vial. So both the loss by sampling and the leakage of N2 and O2 has to be taken into account when calculating the true rates of oxygen consumption and nitrogen production. Now that to set these numbers in the KINCALC, we need to use different standard vials. To set the sampling loss, the best way to do that, and you should start with that, to set the sample volume, you should start with an air standard. A vial with air at 1 atmosphere pressure equal to the standards, but without liquids. You can have liquids in it if you like, but then you will have to write the correct liquid volume into your material sheet so that it ends up here. But in this case, it's an empty vial with just an air standard. Now, in an air standard, since the initial concentration of oxygen and nitrogen is very high, the leakage is negligible, but the sampling loss is not. Now, in order to enable you to set the sampling volume, which you will see here, which is an essential parameter, I've made 2 columns in the spreadsheet, which are the concentrations that are adjusted for leaks and losses. And in a standard, they should be stable if leaks and sampling dilution are correct. Okay, so we can start with illustrating this for nitrogen. I plot the 2 together. So the left one is what we measure in each sampling, and this is the one compensated for the sampling. So I plot these 2 in the same graph. And now here is the measured, and here is that compensated for the loss. It looks quite stable, but that's just because of the scaling. Because so remember that if I now set the sampling volume to 0, the 2 curves are identical. I haven't stolen anything, there is nothing to compensate for. But in this, the default value here is 0.9, and therefore I stabilize my compensated concentration. This is just an intermediate calculation that helps you to set the right value for this one. In order to see it more sensitively, we take this away. So we look at the curve here, and we can put in a trend line. Notice the scaling here. It looks dramatic, the noise here, but it's actually marginal change. It goes from 780,000 here to 790,000. But it's still, there is some decline. So if I now say that my sampling volume is 0.92, I've almost stabilized it. And then if I have now 9.325 or 0.5, it's practically stable. And of course, if we format the axis here and you see, put 0 here, you see that you have a completely stable level. So if we can move this to oxygen, and you see that we've practically stabilized the oxygen as well. It should be the same for the oxygen and nitrogen. You may have slight differences between these two, but essentially this is how you do it to get the right sampling volume for each sampling. Once you have set the right sample volume, you can use a vial with low initial concentrations of oxygen and nitrogen in order to set the right oxygen and nitrogen leakage. Because when the sampling volume is right, and it's right for this vial as well, the two parameters here will determine the stabilized concentrations of oxygen and nitrogen. So we have already in this sheet here imported the high standard, which has not impressively low initial concentrations of the two, because the person who made this experiment has been sloppy about helium washing, but it still is low enough to estimate the leakage. So we can start with oxygen, and we do the same exercise again. We plot the graph here, and we may fix one of the values just for the sake of illustration. Remember that if you don't have any fixed numbers on the minimum and maximum here, you will have it will never stabilize. The figure will never stabilize. Oops. Like that. And then we take this one can be, it doesn't matter. Oops, sorry. Like that. So we fixed it. It's just to illustrate to you what happens if I change the oxygen leak. If I say that I don't have any oxygen leak at all, take 0, it goes up, it goes out of the plot, so I'll go back to 1000 again, and I have a reasonably stable level. If I say that my oxygen leak is 1200, you see that the concentration is going down. So 1000 is probably a reasonable leakage of oxygen. Now you do the same exercise with nitrogen, and in theory nitrogen leakage should be 3 point something times the oxygen, but you can't trust that, because the reason is that if your leakage is through polymers, the oxygen diffuses faster than nitrogen, so it's not necessarily the same relationship between nitrogen and oxygen in the leakage as you have in air. So we can fix this just like that. Oops. Reset this one. Should be like that. I'll fix this one like that. And now you see I have my leakage of nitrogen seems to be too high, because it's compensated for too much leak, so maybe 3500 isn't so bad. Yes. 3700. You can calculate this directly from the readings as well, but exactly. Yeah, 3700. That's too much. So 4 is probably better. Sorry for being clumsy here. P4 like that. Yeah, it's reasonable. We could probably be slightly less. 350. Yeah, it's in the ballpark. The essential thing here is that you stabilize this level in a vial with low concentrations, and you have the reasonable leakage. Remember that in some experiment you may experience that you get drastic leaks after a while in the control vials. Now in that case you're in some trouble, but you can use the first values to set the standard leakage, and then you have to inspect each of the other vials to see if you have similar dramatic increases in the leakage. Most of the cases you don't. Now we're almost there. There is only one more thing that you need to set, but that requires that you have some active organisms which consume oxygen, or you have to guess on this, and that is zero offset for oxygen. For the same reason as we have leakage into the system, you never have a zero reading for oxygen. When you pump a sample from the vial and into the GC, there will be some trace of oxygen leaking into the system. That gives you a zero offset. That means that you will, even if the flask is completely free from oxygen, you will have an oxygen peak. And we need to know that value. And in order to see that value, we need to look at one vial with cultures that consume oxygen and consume oxygen aggressively. So now we are ready to look at the experimental data, so we can start with vial number 1, which is an experiment with Flavobacterium, and I've already prepared a graph over here which is taking the data of, as I showed in the previous video, the simple plot. It's the measured amounts, but it's accumulated into production. But it's not plotted here. Yes, it's accumulated N2, but this doesn't produce any N2. So, and we use this as an example to illustrate how we can possibly set the zero offset value. If you look at the ppm values of oxygen, they start at a trace of oxygen. This was an experiment intended to be anaerobic to begin with, but you never reach zero by helium washing. So it starts at 980 ppm of oxygen, and then it's going fast down during the first few hours, down to very low levels. If you look at the oxygen peak, it looks somewhat different. This is how the oxygen peak looks. If we make an XY graph of it like this, you see that it reaches a level which is not zero. It is around 18,000, or slightly above 18,000. This is how you set the value and the zero offset value, because this is essentially your zero offset. You can now watch what happens if I change the zero offset value. You watch the calculated ppmv of oxygen. If I set it to 0, I'll give high concentrations of oxygen. I get 70 ppm, right? So that is because it doesn't subtract the zero offset value. If, on the other hand, I assume that the zero offset value is 20,000, which is higher than some of the readings, I start to get negative oxygen concentrations, which doesn't make much meaning. So the point is 18,000 is a reasonable number for this experiment and for this robot, for this calibration. It doesn't mean that I claim to know exactly what the oxygen concentration is here. This is where we are in the we are measuring oxygen concentration reasonably down to approximately 10 ppm with the robot. Below that, the only thing you can say is that it's below 10 ppm. But mind you, 10 ppm is extremely low concentration. If you look over here and look what it means in terms of concentrations, it is something like, let's see, it's, if we have this value here, if we go into this table here, the concentration is 27 nanomolar. So it's definitely an extremely low oxygen concentration, so it's acceptable, and we have to live with this. Final words, just to illustrate what this leakage means and the sampling loss. We can make a simple graph of the oxygen, and I'm not interested in nitric oxide, but I make a graph like this. I'm interested in oxygen, but I'm interested in the accumulated N2. No, sorry. So I take this here and move it over to N2. This is now the accumulated N2 production, and I can take this graph back to the calibration set here. And you can now see that since I have the right sampling volume here, the culture is producing, this is the NO and this is the N2O. So after 18 hours, all the nitrogen oxyanions are gone, seen by the depletion of NO and N2O, and N2 reaches a stable level. Now, if I hadn't set the right sample volume here, I would say see a completely different curve. My accumulated value will reach a maximum and then go down with sampling loss, simply because I don't account for the sampling loss. Similarly, if I had ignored the leakage of N2, I'm not 100% sure that you will see any response of this. Yes, you will see it. If I ignore the leakage of N2 into the system, you will see that my accumulated estimated N2 production isn't stable anymore, but it's increasing. So that shows you how essential it is for the nitrogen balance in an experiment to have the sample volume and the nitrogen leakage correct.